There are 5 people. Each of these people or persons has a key and a wristwatch. And these keys and wristwatches are jumbled together and given to a psychometrist. And we asked, so the psychometrist has a responsibility to match the keys with the correct wristwatches. And we are asked, if someone was to try and do this randomly, what are the expected number of correct matches that person would make? And the other question we want to answer, what is the probability that the person will make exactly one correct match if they were to do this matching process randomly? First question we want to ask, what are the total number of ways or possible combinations in which these keys and wristwatches can be mapped together? So the first key could be mapped with 5 wristwatches, the second one with the 4 remaining wristwatches, the third one with the final 3 remaining wristwatches, and so on, which gives us a total number of ways of doing the matching process as 5 factorial, which has a value of 120. So, in order to work out this expectation of the number of correct matches, it's helpful to try and draw a table. So the total number of correct matches could either be 0, 1, 2, 3, 4, or 5. And for each of these, we want to write down the total number of ways in which those correct matches could happen. And we should expect that these 6 numbers should add up to the total number of combinations which we have worked out to be 120. Let's start with 5, as that's the simplest. Of course, because there's only one wristwatch corresponding to each key, there is only one way in which every single key can be mapped to the correct wristwatch. Looking at 4, there are 0 ways in which 4 keys can be mapped to the correct wristwatch, because the final incorrectly mapped one can only map to the correct one, so that's a contradiction, and hence there are 0 ways in achieving exactly 4 correct matches. Looking at 3, so now we want 2 of these keys and wristwatches to be correctly mapped, if we look at the diagram, 3 of them, and 2 of them incorrectly mapped. So the number of ways we can choose the correct ones out of a total of 5 is 5 choose 3. And the ones which are incorrectly mapped, they are just a swap of one another, and there is only one way of doing that. So our answer we can expect is 5 choose 3 times 1, which is just a value of 10. Okay, now let's look at how many ways there are to achieve 2 correct matches. So now we want 2 correctly matched and 3 incorrectly matched. There are 2 ways of choosing the 2 keys which will be correctly mapped. And the question we want to ask is how many ways can the 3 remaining keys and wristwatches be incorrectly mapped to one another? And of course, with only 3 numbers, we can see by inspection there are only 2 ways in which those could be mapped to one another to be incorrect. So hence the total number of ways we can achieve exactly 2 correct matches is 5C2 times 2, which has a value of 20. Finally, let's look at how we can achieve exactly 1 correct match. So we have 1 correctly matched key and wristwatch, and the remaining 4 are incorrectly matched with a wristwatch. So how should we go about this? Let's concentrate on how many ways we can achieve exactly 0 matches between the remaining 4 wristwatches and keys. So the total number of ways in which the keys and wristwatches can be mapped, as we have shown earlier, is now 4 factorial for these 4 keys and wristwatches. And we want to subtract the number of ways in which we can achieve 4 matches, 3 matches, 2 matches, and 1 match to work out the total number of ways there are exactly 0 matches, i.e. all are incorrectly matched in these 4 keys and wristwatches. So 4 factorial is 24. 4 matches, of course, is only one way, because there's only one way each key can be mapped to the correct wristwatch. The 3 matches will be 0 using the same argument as before, because the one key which is meant to be incorrectly matched has no other option but to match the correct one, which is a contradiction. The 2 matches is 4C2 times 6, because there are 2 ways in choosing the correct ones to be matched, and the remaining 2 have only one way of incorrectly matching them, which is by swapping them. And the 1 match, there are 4C1 ways of choosing the wristwatch and key which are correctly matched, and 2 ways in which the remaining 3 can be incorrectly matched, which has a value of 8. So putting all of this together, there are 9 ways in which we can achieve 0 matches for the 4 remaining keys and wristwatches, and 5 choose 1 ways in which we can choose the correct key and wristwatch to be paired together. So 5C1 times 9 has a value of 45. Now to work out how to achieve 0 correct matches, we can simply do 120 minus all the other values, because we know all the numbers must add up to 120, and we save ourselves a bit of a headache of working this out by brute force. Now let's convert all of these numbers to probabilities. And the way we can convert a probability is by dividing each one by 120, the total. Okay, so the question asked us to work out the expected number of correct matches, which is now quite easy because we've got the discrete distribution for this probability mass function. So the expected number of correct matches now will be each of the number of correct matches multiplied by its probability. Since all of them have the common denominator of 120, we can move that directly to the denominator of the whole fraction. And plugging into these numbers, we get an answer of exactly 1. So if someone was to do this process randomly, they can expect to get 1 correct match between a key and a wristwatch. The other part of the question asked us, what's the probability of getting exactly 1 correct match? Now this is pretty straightforward from our table, as we can already see the probability is 45 over 120. But let's simplify this value and we get an answer of 3/8. Thanks.